Hello everyone, this is Ramnesh Kumar Sahu, and today we are going to talk about Boolean Algebra, part of computer science. As we know, there are two components of a computer, hardware and software. So Boolean Algebra is related to the hardware component of a computer. Before starting, I would like to ask you a question. What is a computer? Think about it. It is an electronic device which takes input, processes it and gives the output. Now focus on the word an electronic device because there is a big difference between electrical and electronic devices. As the devices without voltage regulation are called electrical devices. Example, electric fans, tube lights, light bulbs, etc. And the devices with voltage regulation and having the basic unit as an IC or integrated circuit are called electronic devices. Example, the circuit used in air conditioners, all the digital devices, calculators, smartphones, computers, and many more. Now, what is an IC or integrated circuit? Many of you have seen a black box-like structure on a circuit board with some code written on it. So that is the IC or an integrated circuit. It is made up of gates, and gates are made up of resistors. And by very high level integration, resistors have been reduced into size to transistors, and transistors are made up of capacitors, which are the basic storehouse of charges, as the data in an electric circuit is stored in the form of charges only. Now, here comes the main part of our lecture. What is Boolean algebra? So, Boolean algebra is a mathematics or mathematical tool invented by George Boole to solve logical functions. It is also known as switching algebra. It is used to design the circuit of an integrated circuit. It is based on the binary digits or bit values which are 0 and 1. Now, here we are talking about logical functions. So what is a logical function? A logical function or Boolean function are those functions which give output as true or false. True for 1 and false for 0. These values are also known as truth values. Now, a table containing all the possible combinations of truth values of a logical function is known as the truth table. And truth table is used to predict the output of a Boolean function in certain set of inputs by the user. And those inputs are in the form of 0 and 1, high or low value. Here is an important note. The trick to find the number of combinations of truth values which are possible for a logical function where n is the number of literals in an expression. Here comes the formula 2 raised to the power n, where n is the number of inputs or variables which has to be input by the user. Now here are two terms, tautology and fallacy. If the result of a logical function is always true, then that condition is known as tautology, and if the result of a logical function is always false, that condition is known as fallacy. Now here is an representation of the usage of the formula 2 raised to the power n to find the combinations of truth values which are possible for a logical function, where n is the number of literals in an expression. Now here in this case there are two literals x and y. Here three literals x, y and z, and here four literals a, b, c and d. So here are the steps to create a truth table. First of all, find the value of 2 raised to the power n. So 2 raised to the power 2 in this case is equal to 4, 8 and 16 in the following cases. Now let p is equal to half of 2 raised to the power n. So here half of 4 is equal to 2. So write 0 2 times and write 1 2 times, where it is the half of 2 raised to the power n. So in this case 2 times 0, 2 times 1. Now again half the value of p, then it would be 1 in this case. So 1 times 0, 1 times 1. We have to do this until we get the last column as 0, 1, 0, 1, 0, 1, as you can see in all these cases. Now, as we know, an expression or an arithmetic expression or algebraic expression contains certain variables or values along with the operators. And in Boolean algebra, we also require variables which we have learnt in the previous slide And here comes the operators, which are known as logical or Boolean operators. So they work on truth values of a logical function and return output in the form of true and false only. Now in Boolean algebra, there are three logical operators which are not, and or. So first of all, we will talk about not operator. So not operator basically means the complement of the input, which is represented by x apostrophe or x bar. So it is an unary operator which consists of one input and one output. The output will be true if the input is false, and the output will be false if the input is true. It is vice versa process, and here is the complement and the reverse value of the input. So as we can see in this truth table, if the user has input the value as low, then the result will be high. If the input is high, the result will be low. Now second is the AND operator, which is also known as the product operator in Boolean algebra. So it is a binary operator which consists of two or more inputs and one output. The output will be true when all the inputs are true. Remember, when all the inputs are true. If in any case one input is false, then the output will be false. So as in this case, there are two variables. When all the inputs are true, the value is also 1 or true. And here in this case, if any one of the input is false, the value is false or the output is false. Now here comes the OR operator or the summation or addition operator. It is a binary operator also, which consists of two or more inputs and one output. The output will be true if any one of the inputs is true. In this case, any one of the input is true, then the output will be true. Like here we can see 0, 1, the output is 1. 1, 1, the output is also 1. 1, 0, the output is even 1 also. And in this case only one case, when all the inputs are false, the output will be false in the case of OR operator. Now here are 5 questions related to creating the truth tables for the given Boolean functions. So we will look after them. So here is the first question. So as in the question, it is x complement into y into z plus x into z whole complement into y complement plus z complement. So first of all, we will look after the number of literals. So here there are three literals x, y and z. So we will apply the formula to find the combinations. 2 raised to the power 3 is equal to 8. So 8 combinations can be formed through these three literals. So we will have the 8 value of 8. It will be 4 times 0, 4 times 1, then 2 times 0, 2 times 1, then 0, 1, 0, 1. Then we will separate the terms and individually write the values. Like here it is x complement, so value of x complement, y complement, z complement, all the values which we will require in this Boolean function. Then we will solve them, or we will apply the logic by the OR operator and AND operator. Like here we have used OR operator. So if any one of the input is true, the output will also be true. And here in this case it is the AND operator. If all the inputs are true, then the output will be true. And finally we will get the result of the Boolean function, 8 combinations of the output. Similarly, you can pause the video and look at the truth tables of the following questions. Here just I have changed the Boolean function variables into ABC. You may choose any of the variable of your choice. It just means the input by the user in the form of 0 and 1. Now here comes the important part of the Boolean algebra, Boolean identities and laws, which will be used to convert one form of Boolean algebra into another, from product of sums to sum of products, which we will be learning in the upcoming slides. And to solve the Boolean functions by applying these identities and laws, these are important. Now first comes the property of 1. 1 plus x is equal to 1. 1 into x is equal to x. So here in this table, x, y, z are also the variables or the inputs by the user in the form of 0 and 1. So 1 plus x is equal to 1, 1 into x is equal to x. Property of 0 says that 0 plus x is equal to x, 0 into x is equal to 0. Now idempotence law. Idempotence law says that x plus x is equal to x and x multiplied by x is equal to x. Now complement law, x plus x naught is equal to 1, x into x naught is equal to 0. Now involution law, which says that x double complement is equal to x or x double not is equal to x. Commutative law, it is similar as in mathematics. X plus y is equal to y plus x, or a plus b is equal to b plus a. X into y is equal to y into x. Now absorption law, as we can see here, the value of x is being dominant over y. So x plus xy is equal to x, and x into x plus y is also equal to x. As if we will open the bracket, x into x, by idempotence law it is also equal to x, and then x plus xy, which is already the result here as x. Now associative law, x plus y whole bracket plus z is equal to x plus whole bracket y plus z. And similarly, the associative law for multiplication, that whatever we solve first will never change the output or the result. Now distributive law, here it is, this one is similar to the law which we are using in mathematics. By opening the bracket it is xy plus xz, but here in this case it is x plus yz is equal to x plus y into x plus z. We will be using distributive law to convert one form of Boolean algebra into another. Now here it is the most fascinating law, De Morgan's law, with a very catchy phrase, break the line, change the sign, which will be applied in the questions like this. If x plus y whole complement is present, we will break the line here, and it will be distributive among the individuals or the individual inputs, x naught and y naught. Similarly, x naught and y naught. And the change of the sign, plus into multiply and multiply into plus. Now here comes the next topic, circuit diagram. Now as we have seen, we have been using the operators to solve the functions. Now here comes the gates. Now what are gates? Gates are the pictorial representation of the operators which we are using to represent a given Boolean function in the form of a circuit diagram. So pictorial representation of the function is known as a circuit diagram of that function. So in Boolean algebra we are having logic gates which are of three types: basic gates, universal gates and special gates. So first of all we will learn about basic gates, which are not, and or. So here is the precedence of operators, which states that we will give first preference to not, then and then or. Now here is the representation, diagrammatically representation of basic gates. It is the NOT gate, AND gate and OR gate. As we can see, NOT gate is a unary operator or unary gate, so it will take one input and one output, which will be the complement. Here it is the product and here is the sum. Now here is the question to draw a circuit diagram of the given Boolean function, which is x complement y into z complement plus x into y whole complement into x plus z complement. So here is the circuit diagram of the given Boolean function. First of all, we will identify the number of literals used in the function, which is in this case 3, x, y and z. So we will write x, y and z and draw straight lines parallel to each other. Okay. Then as in the question, we are having x complement, so we will use the NOT gate to find the complement of x, and here comes the y, which is directly joining by the AND operator. Then z complement, similarly we will draw and use the NOT operators, AND operators and OR operators or OR gates, and then we will get the desired result. And as in this case, these are the sum of products. Okay, so for the sum we will use OR gate. So we will combine all these terms by the OR gate, and we will finally get the output or the result. Now here is the topic, forms of Boolean algebra. As I have been saying, sum of products and product of sums, so these are the forms of Boolean algebra. Now there are two forms, standard form and canonical form. So we will be dealing with standard form in this video. So sum of products and product of sums are the part of standard form of Boolean algebra. So sum of products means the individual terms will be in the form of products and overall they will be connected by sum. And in product of sums, the individual terms will be in the form of sums and they will be connected with each other by the product. Now distributive law plays a major role in converting SOP to POS and POS to SOP. By applying these laws, like x plus yz is equal to x plus y into x plus z, and then x bracket y plus z bracket closed is equal to xy plus xz. And if we will look at the single variable or single term like x, it can also be represented as x plus 0 or x multiplied by 1. Now here is the question to convert this given Boolean function into SOP and POS. So first of all, we will convert it into SOP by applying distributive law, as SOP means sum of products. So as in the first term is also in the already in the form of a product, so we will leave as it is. Then here it is in the form of like some sign is also being coming, so we will remove it by opening the bracket. It is x y naught into z plus x z into z, and by idempotence law z into z is equal to z. So we have converted it into SOP. Now the second form is the POS form. So we will apply the distributive law, this first part, which says that x plus yz is equal to x plus y into x plus z. By applying that, we will get the result as POS, or product of sums. Now here is the universal gates, which are of two types, NAND and NOR gate. So NAND gate is the combination of and NOT gate, and NOR gate is the combination of OR and NOT gate. So these two gates are called universal gates because any gate can be replaced with them. That means instead of using NOT gate, AND gate and NOR gate, we can use NAND and NOR gate universally in the place of any of the gates. So NAND gate is basically used with SOP or sum of products, and NOR gate is used basically with POS or product of sums. So here is the representation of these two gates. First one is the NAND gate, second one is the NOR gate. As we can see, the part of NOT is being represented by the circle, and rest is the AND gate, and here OR gate plus part of NOT gate. So if in case we have only one input or one variable in the form of x or y, as NAND and NOR gates are binary, so we will split its ends to make it look like it has been divided into two parts, and in this case it is binary. So it will even then it will represent the output as the complement of the input. Now here are two questions which have to be solved by NAND and NOR gate. So here we have used NAND gate because the question was in the form of SOP. So we will replace each and every gate with NAND and NOR gate, and as we are using NAND gate, so we will follow the same process, as x and y will directly come, and then the product will be represented by the NAND gate. Then here in this case, like x has been complemented, so we will first complement it to make a NOT, or the reverse of it. We will split it end, and it will behave like a binary, and then we will get the result as x naught. Okay, similarly we will combine all these together with the NAND gate, but the purpose of NAND gate is to make a product. Okay, so we will get the product with a whole complement. So by applying De Morgan's law, we will convert it into SOP from like here is the product, and we will convert it into SOP. So double NOT, so by involution law, xy double complement is equal to xy plus x complement y into z complement. Double complement is equal to x complement y into z complement, and similarly y complement into z will eventually come here. So we will get the desired output. Now as in the second question, it says that we are requiring x plus xy plus x complement y into z complement plus z complement. So if we are using x, so similarly we will directly transfer x, as there is no complement of it, so it will directly combine with other of the terms. But if we will do that after applying De Morgan's law, we will get the result as x complement, and here in this case z, and we have been requiring z complement and x. So we can see, as in the question, above which variable we are giving the complement, we are not getting it. And as in this case, where there are single input, where there is single input present, we would be getting its complement where it is not mentioned in the question. So this is a wrong circuit diagram. Therefore, focus on these words. Where single input is present, we would take its complement if not given, and vice versa. That means in the question, if the complement is not given, we will take it complement, we will assume it as it is the complement given, and where there is given the complement we will not take it, or we will just simply join it with other operators or terms. Like, let me show you the correct way. So here it is the correct circuit diagram. So as in this case, in the question, no complement was given over x, but we have taken the complement over x, and by at last applying the De Morgan's law, we will get the desired result as x, and here in this case z complement. Now here are two questions. Okay. First of all, the two questions are of the form and the product of sums, basically. And in the next part we are having sum of products. So sum of products will be solved by NAND gate, and the first two parts will be solved by NOR gate. So as we can see, the first two parts have been solved with NOR gate. You can pause the video and look at it. And on using the universal gates, we have to apply De Morgan's law at every place to get the desired output. Now here are the special gates, which are XOR gate and XNOR gate. So these are exclusive OR gate and exclusive NOR gate respectively. In the case of XOR gate, output will be high if number of high inputs are odd. And in the case of XNOR gate or XNOR gate, output will be high if all the inputs are low or number of high inputs are even. So these are diagrammatically represented by this shape, the combination of OR gate, and this curve has been represented as the exclusive one. And as the case of OR gate, it will be the sum or addition and a circle over the plus sign. And here circle over the plus sign with not, as not is also been included, so it will be a complement over it. And by applying De Morgan's law, we will break the line and change the sign. So these two were the parts of the OR gate only, the exclusive OR and exclusive NOR. Okay. So here are the truth table for XOR gate. Here in this case 2 variables, 3 variables. Then if the inputs, as we have seen, if the output will be high if the number of high inputs are odd. As in this case, the number of high inputs are odd, so that's why. Here in this case, the number of high inputs were even, so the output is also 0 or low. Now here was the truth table for XNOR gate or XNOR gate, where if the output high input are even, the output is true, or if all the input is false, the output is also true, and rest in other cases it will be false. Now here is the principle of duality. So principle of duality states that a function can be derived from another Boolean function by changing AND sign into OR sign, 1 into 0, and vice versa. If in the question or in the Boolean function AND sign is present, it will be converted into OR sign to find its dual, or by applying principle of duality, 1 into 0. Like we can see in the example, as it is the complement law only, x plus x naught is equal to 1, which has been converted into x complement is equal to 0. As in this case, plus has been changed into multiply sign and 1 has been changed into 0. Similarly, x plus y into z, so plus has been changed into multiply, and multiply has been changed into plus. And in this case, plus has been changed into multiply and multiply has been changed into plus, and then plus into multiply. Similarly, we will apply the principle of duality in the given Boolean functions to find its dual. We will call the resultant as the dual. Now here is the complement of Boolean functions. To find the complement of a given Boolean function, we will apply the De Morgan's law because we will require to take the whole complement of the given Boolean function. So here is the question: find the complement of the following Boolean function: x complement plus y plus z complement multiplied by y plus z plus x into z complement. So we will take the whole complement, then we will break the sign and apply the not sign on the individual components or individual terms. Then here we will also then again break the line and change the sign. So plus has been changed into multiplied, plus has been remaining the same as it has been already changed from multiplied to plus. Then x double naught is equal to x by involution law, y complement will come, then z double complement is equal to z, y complement, z complement, then multiplied by x complement, and z double complement is equal to z. So here we have find the complement of the given Boolean function. So that's all in this video. I hope you like this video, and that was all about Boolean algebra in one shot. Thank you.